What do nonlinear differential equations, neurons, and electrical circuits have in common? Well, let me welcome you to the Hodgkin-Huxley model. And in 1952, the researchers Hodgkin and Huxley came up with this model to analyze how neurons propagate their signal, their action potential to other neurons, and they also look at how these propagations are modeled in the neuron. At the core of the Hodgkin-Huxley model is something familiar yet unexpected, an electrical circuit. Hodgkin and Huxley conceived a way to map the neuron's action potential onto an electrical circuit, where the membrane itself acts like a capacitor, capable of storing and releasing electric charge. In this model, ion channels serve as pathways for charged particles, much like resistors in a circuit. The flow of ions, sodium, potassium, and a bit of leakage current, mostly from chloride ions, translates into currents that change the cell's membrane potential.
To bring this concept to life mathematically, the HH model uses a set of nonlinear differential equations that evolve from this circuit analogy. The differential equations capture the changing voltage across the neuron's membrane and link it to the flow of ions as they move through specific channels. It is here where it gets interesting. The sodium and potassium channels are voltage gated, meaning they open or close depending on the membrane potential, much like a light switch with a voltage trigger. This interdependence is at the heart of the neuron's explosive response to a stimulus, generating the iconic spike of the action potential.
Each ion channel is represented by a conductance parameter, which controls how easily ions flow. These channels are gated by variables, which represent the probability of the channels being open at any moment. Imagine these as tiny doors that can swing open or closed, modulating the current depending on the membrane's voltage.
As the membrane potential changes, the gates respond, allowing sodium to rush in or potassium to flow out in a carefully timed sequence. This creates a feedback loop that drives the action potential.
Here's where bifurcation analysis steps in to add a whole new layer of understanding. By adjusting parameters like the input current or channel conductance, we can witness dramatic shifts in a neuron's behavior. These shifts, known as bifurcations, act like turning points in the system. Think of them as thresholds. If you increase the current just enough, suddenly the neuron leaps from a resting state to firing repetitively. This is where the magic happens.
In the context of the HH model, bifurcations allow us to explore three different things. The first thing is the transition to firing. Secondly, different types of neuronal excitability. Different bifurcations explain why some neurons respond readily to tiny currents while others need a stronger stimulus. And lastly, the stability of firing patterns. Bifurcation analysis can tell us whether a neuron's firing will be stable or if it will switch back to silence depending on its inputs. Our project used bifurcation analysis to uncover how a neuron's response could vary across different levels of input current. These explorations help us visualize when a neuron might fire, rest, or even enter oscillatory cycles.
Now that we've introduced the basics, let's dive further into the dynamics and take you along our analysis. In our research, we modeled two distinct neurons by adjusting their initial conditions. For the first neuron, we adhered to the industry standards, utilizing most parameters from the original 1952 Hodgkin-Huxley paper. These values are commonly used for the giant squid axon, a preferred model due to its large size and well-documented characteristics. This established model served as our foundation to observe neuronal behavior as we varied a single parameter.
To investigate one-dimensional bifurcations, we choose to alter the input current, which is the most commonly used bifurcation parameter in neuronal studies. By constructing the model using the nonlinear differential equations and applying the Euler method for numerical integration, we simulated the neuron's response to varying input currents. We then systematically varied the input current, examining the spiking responses and phase space reactions to understand the neuron's behavior under different stimuli. Focusing on the first neuron, we observed a distinct bifurcation as the input ranged from 0 to 20 microamperes per square centimeter. Initially, the neuron exhibited sub-threshold oscillations, small fluctuations in the membrane potential that don't trigger action potentials. At an input current of approximately 2.3 microamperes per square centimeter, The membrane potential crossed -60 millivolts, causing an abrupt change and starting a spike. However, only one spike starts and dies out quickly. As we further increase the input current, the neuron doesn't immediately settle into a regular spike train. Instead, it encounters the threshold, resulting in a brief series of spikes that eventually damped out. Once the input current surpassed this critical value, a continuous spike train emerged, signaling a stable firing pattern. Here, we identify the saddle node bifurcation. The attractor vanished, and the phase space began to display oscillatory behavior, a clear indication of this type of bifurcation.
Continuing increasing the input current, we observe the spiking amplitude decreasing until the cycle collapsed on itself, resulting in what's known as a fault limit cycle. This phenomenon led to the end of spiking, as the neuron returned to a stable, non-firing state. We applied the same methodology to a second neuron model, inspired by research on frog axon spiking behavior. This model incorporated experimentally determined variables. The spiking behavior here was significantly different. Slight variations in input current elicited quicker and sharper responses. Even at very low input currents, the spike train began almost immediately, unlike the first neuron, which required a significant input to start firing. In this neuron, a Hopf bifurcation was evident. At an input current of 0, the neuron fired a single spike, indicating heightened sensitivity. Increasing the input current just below 1 microampere per square centimeter quickly ramped up the spike frequency. However, as we continued to increase the input current, the spike train rapidly damped out. The phase space revealed the unit circle collapsing on itself, a fault limit cycle, resulting in the termination of spiking once again.
We also examined phase plots for both neurons, clearly observing that the intersections of nuclein lines indicate the location of attractors. This is what you would expect from attractors in phase space. Do these contrasting behaviors we observed actually mean something biology-wise? We can connect this to differences between type 1 and type 2 neurons. The first neuron, exhibiting a gradual onset of spiking, typically belonging to a saddle node bifurcation, behaves more like a type 1 neuron. These neurons can modulate their firing rates smoothly in response to a wide range of stimuli, allowing for nuanced control. Conversely, the second neuron mirrors behavior of a type 2 neuron, which responds sharply and sensitively to input currents, firing action potentials almost immediately. These neurons are crucial for rapid responses, such as sensory neurons that detect changes in the environment, like pain or touch receptors.
In these plots, which show spiking frequency against input current, we can clearly see the differences between the two neurons. One exhibits a larger, more gradual response, while the other responds in a much sharper and quicker manner. Let's delve into the final aspect of our project, codimension 2 bifurcations in the Hodgkin-Huxley model. In our analysis, we explored what happens when we simultaneously adjust two parameters, rather than one, to observe how the neuron's excitability states transform. This allows us to look at codimension 2 bifurcations. These are critical points where behavior can converge or diverge based on combined parameter changes. In our project, we focused specifically on how the neuron's excitability changes as we tweak two parameters together. We used the applied current and the ion conductance.
In our first diagram, we've mapped out three regions: yellow, teal, and dark purple, each one representing a different type of response. These aren't just colors, they are distinct types of neural behavior, separated by the boundaries where codimension 2 bifurcation can happen. Along these edges, even the slightest shift in either parameter can flip a neuron from one state to another. Next, you can see a zoomed in image showing a smoother boundary between these behaviors. We did this for both the sodium conductance and potassium conductance. In both plots, we can identify three types of regions, showing either zero spikes, showing damped out spiking less than 5, or spike trains more than 5 spikes in 200 milliseconds.
We plotted these in 3 dimensions, with the z-axis representing spike counts. Here we see that a neuron behaves nothing like a simple switch. We can see this constructed landscape. This landscape shows the versatility of neurons. Since this is only 2 dimensions and the full model comprises more dimensions, this dependence on many different variables allows a neuron to respond differently to the many combinations of parameters.
So for the past 2 weeks we've been really busy looking and deep diving into the HH model and the neuronal dynamics attached to it. And we can't say anything else than it has been really fascinating. The topic is really interesting and really broad, and it's really cool to see how it's both relevant in the field of biology as well as in mathematics. And I think it was really cool to see these bifurcations reappear in a biological context. And yeah, over the past 2 weeks we only saw the tip of the iceberg, and so we can recommend it to you all to dive deeper into it.